Hi there, I am going to be taking you through everything that you need to know for separating substances for GCSE chemistry. This is kind of aligned to the Cambridge exam board for students that are taking their exam in 2022. There's plenty, however, that is in common because this is one of the earlier topics that chemistry GCSE students will be studying. So there's something for everyone here, and what I'm going to do is, in as quick a time as possible, I'm going to be highlighting the areas that you need to concentrate on when you are revising. The first thing that we're going to do is we're going to start talking about what these terms mean. So a mixture is any substance that you have which contains more than one substance when you kind of look at it, so, at a closer level of detail. So let's say, for example, air. Well, air is most people say, right, okay, air is a substance, but in actual fact, air is a mixture of different gases: nitrogen, oxygen, water, carbon dioxide, argon. There's lots of other substances that actually make up air. And you don't have to go too far in your homes to find other mixtures. The thing that we're going to be focusing on mainly in the first part of this video is what actually happens with solution. So a solution contains a solid that has been successfully dissolved in a liquid. Solution then forms. So what actually happens? The solid doesn't just like disappear completely, as if by magic. It doesn't do that. What actually happens is, in the original solid, you've got forces that are attractive, and the solid particles just stick to one another. Okay, but what then happens is, if you actually have a solvent coming along, the solvent actually prizes and breaks off the solute particles. In this example, it's sugar, and they provide an alternative set of particles that have this attractive force. So you'll find that the sugar particles have more attractive force towards the solvent particles than they did when they were originally in a solid solute, and that basically is the reason why some things dissolve. Now, some things dissolve better than others. The liquid, by the way, is called a solvent. So solute plus solvent gives you a solution. It's a very, very useful shortcut to remembering what is actually happening and what's doing what. So not everything actually does dissolve very, very easily. Got a range of compounds, and this term over here, mass in grams dissolving in 100 grams of water at 25 degrees centigrade, is actually a term called solubility. Let's write that down. So you can actually see that these numbers are very, very big, and what's actually happening is that they're getting smaller and smaller and smaller until you've got very, very little numbers here. So you can actually class these ones as being very soluble. So these are chemicals like silver nitrate, calcium nitrate, sugar is in there as well. You've got chemicals like calcium hydroxide. Once you get to this kind of range, you can actually call them sparingly soluble. Sparingly means hardly, very, very little. You can go even further, and when you're talking about these numbers of so little, with such small values, that we're not able to class them as sparingly soluble anymore. We just say that they are insoluble because there's so little that will actually dissolve. And you've got to think, well, something like silver chloride, why is it virtually insoluble? The reason why is because even though you've got these water particles that have the ability to form attractive forces between themselves and the silver chloride particles, namely the silver ions and the chloride ions. However, the attractive forces between the silver chloride ions is so strong that it just doesn't succeed at all. Maybe it might succeed for very, very few of them, but relatively speaking, but it doesn't for the vast majority. So that's the reason why we have very little dissolving, and we class them we class those salts as and substances as insoluble. Okay, what is a saturated solution now? A saturated solution effectively can't hold any more solute inside it. So you can imagine that you've got um, solvent particles. Okay, so solvent particles you can imagine surrounding a solute particle. Okay, so I can just put that there. All right, and you get to a stage in the saturated solution, so there's attractive forces. You get to a stage where the solute particles cannot be held by any more solvent particles, because all of the solvent particles are already holding solute particles inside it. So when you get to that stage, you have a solution which is saturated. Now, how can you change that? Well, one thing that you can do is you can heat it. Okay, so if you heat it, what then happens is your particles in the solution start to move around even faster. So you're giving them more kinetic energy. And in effect, what you're doing is you're providing them more energy to actually cope with with dissolving more solute particles. Okay. And the reverse can happen as well. If you actually have a warm solution and you cool it down, the solute particles can't stay in the cooling solution, and so what happens is they're just dumped out of solution, and that would actually then mean that you can sustain a saturated solution. It still stays at saturated, but the amount that can actually be dissolved in that saturated solution is much smaller when it actually cools down. So from a situation where you've actually got all of the solute dissolved, you can actually, by cooling it down, still have a saturated solution, but you actually then find that some of the solute will actually come out and it will settle at the bottom of your container. Now, that's actually quite a useful method of separating out a solute from a solution. So what you can do is you can pack um, excessive amounts of solute and warm it, and then start to cool it down. And what you'll then find is you'll then find solids forming at the bottom, and you could actually find crystals as well. And that is a method of separation that we'll talk about later on in the video. So to conclude, things get more soluble when you warm them up. And so when you warm up your solvent, things generally get more soluble. Soluble solids usually get more soluble as the temperature rises, and the solution is called saturated when it can dissolve no more solute at that temperature. So basically, in other terms, what you can do is you can start off with a saturated solution, and if you were to warm that up, you could get to a stage where you have an unsaturated solution. Okay, but if you started off, so that's warming, let me just put that here just to be clear, and that's warming, and that's a rise in temperature. And if you started off with a saturated solution and you then cooled that down, so you lower the temperature, you still have a saturated solution, but it has a lower solubility. And what you'll also get is you'll get some solute crashing out, basically, of solution. And that's actually used as a technique for separation as well. You've also got to be aware of the fact that water is not the only solvent that's out there, and anyone that's tried to remove permanent pen with water will actually understand that as well. So the best way to remove, if you've got a piece of furniture and you've got a permanent pen mark on there. The best way to do it is you just get some hand sanitizer and a bit of tissue, and then you can just dissolve it. Why does that work? Because ethanol actually has more attractive forces towards the permanent pen ink particles than water does. It's as simple as that. These solvents tend to be quite smelly. They actually will turn into a gas very easily. Ethanol is used, for example, in perfumes and aftershaves. So the name that's given to liquids that turn very easily into gases at room temperature is actually called volatile. So we can talk about volatile volatility. So they can evaporate easily. Right, we can move on to thinking about a pure substance. Pure substances actually have very unique properties as well. I mentioned in the previous video in the series that you can actually get very sharp and very clear melting and boiling points if you start off with pure water. This is a representation of pure water, but it's actually simplified. In fact, if you were to have a truer representation of water, then you would actually find that the there will be more water particles that are around. So the truer version of water would probably look like this, where you have a random order and most of the particles you would find have this random order. There's no set lattice. They're all touching, but you would find that around a single particle, most of the surfaces around the single particle are actually in contact with another particle. But there are some gaps. There's one gap here, there's one gap there, there's one gap there. Okay, don't make the mistake of thinking that the water particles have gaps, but we've simplified this just in here. Just think of this as being the top layer, okay, the layer that's right in front, closest to where you're looking. So you can actually see water particles here, and this is something that is not just water particles. You've actually got some other particles. So now this is now not pure at all, because there's more than one type of substance that's in that. Maybe you might actually have an impurity that's quite harmful. So there's a wider context with whether purity matters or not. It does matter. You might actually have something that's that could a chemical in there, for example, that could make you really ill. So it's very important. How can you tell that a substance is pure? The simple thing to do is, if you want to check out a substance and you want to make sure that there's only one type of particle in there, check out its melting and boiling point. So you can access in other resources videos with melting and boiling point apparatus. And basically what it is it's a thermometer, and it's connected to a lens, and there's a little chamber, and you actually just basically put your substance in the chamber and you study it, and you slowly, inside this chamber, you raise the temperature and you keep an eye on the temperature. And as soon as your solid, for example, starts to collapse into a liquid, you can actually study the melting point. And if the melting point still rises, that means that there's a range for the melting point, and it's highly likely that your substance is impure. And what you can do is you can check that against some tables. And these data tables enable you to then think, right, okay, well, I've got a melting point for my substance, and it's exactly how I see it on the data table. So this must be a really pure substance. Very important when we talk about things like medicine, for example, aspirin. The bigger the impurity, the bigger the change in melting and boiling points, and the wider the temperature range over which melting and boiling occurs. So if you have something like pure water will melt at 0 degrees centigrade and it will boil at 100. But if you actually add a little bit of common salt to water, the melting point decreases. So it goes down with impurities, and it actually is elevated with impurities as well. The boiling point, rather, is elevated with impurities. So if you then find that it boils at around about 102, 103, you've actually got an impurity. It's not just pure water. Now, there are a number of different separation techniques that not only you have to be able to describe, you have to be able to draw, and you have to be able to label as well. So the 6 ones that are the most common ones are filtration, crystallization, evaporation, simple distillation, fractional distillation, and paper chromatography. It's a really useful summary for you to compare each of those. So filtration is used to separate a solid from a liquid. Often, more often than not, when you're doing chemistry, GCSE, what you've done is you've actually made that solid as through a saturated solution, or you are actually filtering off something that is insoluble, and you're trying to separate it out from your solution that contains another substance. So, like case in point, trying to separate sand and salt. So that's filtration. Crystallization is something that is used to separate a solute from its solution. You might be wondering, why is it that you've actually got 2 of these? Well, sometimes when you have very low solubilities, it doesn't actually, you don't actually separate out your solvent from a solute to form crystals. You actually find that it just turns into a powder. So something like common salt, NaCl, that would be that would be evaporation, because you can't actually form crystals by doing that method. It's just very difficult. Whereas crystallization would actually be something that's potentially more suitable for something like copper 2 sulfate. Okay. Now, I'm not suggesting that you can't form salt crystals, but I'm talking about a method that you can actually use to separate out the substance. If you really wanted to separate out crystals, you would use you would give it a long time to evaporate out. Simple distillation is a solvent from a solution, so that's actually slightly different to fractional distillation, where you actually have multiple solvents, multiple liquids that are mixed with each other. And it's like as if it forms one gigantic solvent. So you've got liquids that are miscible, and what do I mean by miscible? They mix with each other. So it's very difficult to actually separate them out. It's not like oil and vinegar that actually separates out into 2 layers. So you have to use fractional distillation. More on that in a small while. Paper chromatography is there to separate out substances from a solution that are often colored dyes, but chromatography can also be used with invisible substances that you have in a solution as well. Right, okay, so the first one is actually something that is relatively easy for students to understand, because they've just met it quite so many different times. But you must make sure that you actually refer to the different the different separated substances in the correct way. So filtration requires a filter paper, and the idea behind this is that insoluble substances will be kept behind by the filter paper, and it will form a residue. So you could use a relatively insoluble substance like chalk and dissolved in water. You could filter it through a filter paper. The filter paper will be held by a filter funnel, and it could go into a conical flask. What you have coming through the bottom is called a filtrate. So make sure that you're okay and comfortable with that word. A second method to getting a solute from a solvent is crystallization. And this really works with salts like copper 2 sulfate. So look out for that. A common procedure that they test you on for crystallization is a procedure which involves sulfuric acid and how that reacts with an insoluble base like copper oxide. Essentially, what happens is you make copper sulfate and you heat the sulfuric acid, the dilute sulfuric acid, so that the solubility of the copper sulfate is maximized and you form a saturated solution. And you also ensure that you have an excess of the insoluble base, so all of the acid actually reacts. So eventually, what you then find is you have copper oxide and you have copper sulfate as a solution, and you then use filtration to separate out the insoluble base. So that's step one on the video, and then what you do is you heat up the copper sulfate, and what that then does is it allows you to evaporate some of the water. Now, if just from what we were talking about earlier when we were talking about solutes and solvents and saturated solution, if you actually have evaporation taking place, then what happens is you decrease your volume, and if you decrease your volume of solvent, you actually decrease the mass that it can actually dissolve. So you're actually reducing down the solvent, and you can then get it to a stage where you turn it from an unsaturated solution into a saturated solution. Now, you would do that at that stage. What's very common is that you can actually use a glass rod on the warm in the warm solvent. You actually put a glass rod inside, and when you take it out, you will find that it actually forms crystals. And the reason why it does that is because when you take it out, it cools down, and because solubility decreases with temperature, if it's very close to being a saturated solution, the temperature of the solution goes down, and the solute is thrown out. It basically crashes out of the solution. When that happens, you actually have to stop the heat, because if you kept going, what would then happen is you would actually have not crystals. You would actually have powder, and you would actually lose all your ability to form pure crystals. Sometimes what then happens is if you got that heat, it will actually start to decompose the powder that's around. So you basically stop at that point, and then what you do is you let the solution cool down. Now, as the solution cools down, the solubility goes down. And as the solubility goes down, you then basically have an unsaturated solution situation where you had an unsaturated solution which was at high temperature forming a saturated solution. Now, you can actually see now all of these crystals basically crash out, and then they form a layer at the bottom, and that's quite useful. When it completely cools down, you can then use filtration again to separate that out, and that's the end of the procedure. You then have your pure blue crystals of copper sulfate. You would have a filtrate which is dilute copper 2 sulfate. If you wanted to get more crystals, you would actually then return it back to the heat source, and you would just carry on. So you could just reduce it down, remove even more solvent at a higher temperature, and force it to become saturated again. So that's what you do. There's usually a sneaky step here. If you were in the question, if it asked you for blue crystals, what you'd have to do is you'd have to get something like a paper towel, and you'd have to dab. That's the term. You'd have to dab the paper towel onto and blot the crystals to remove the solution. Then you're left with dry crystals. Sometimes you just have to look out for that. Sometimes that's a little sting in the tail for in an extended question. So I did mention earlier salt, common salt, which is sodium chloride, is an example of a solution where the solubility changes very, very little. So when you have something like sodium chloride, the solubility is actually it doesn't really adjust at all. So crystallization actually doesn't work for these. They don't actually crash out as much as you'd expect, you'd want them to. So in order to just to form salt, a pure sample of salt, if you had salt solution, you're basically trying to remove the solvent, which is water, from salt solution. So that would be salt plus water, or salt water. Basically, what you do is you basically heat it, drive off all of the water, and you actually leave a wonderful layer of salt right at the bottom. It looks powdery. Now, something that's quite unique for Cambridge is the separation of a mixture of two solids. In the sense that if you actually have a mixture of salt and sugar, I'll come to that in just a second. But if you need to separate a mixture of two solids, try and find a solvent that will dissolve just one of them. Okay, so classic example, salt and sand. Okay, if you add water, what actually happens is the salt combines with the water to form a solution, but the sand just stays behind. So if the sand just stays behind, all you need to do is, you guessed it, you just need to filter that off. So when you actually have your filtration, the residue is the sand, and the filtrate is the salt and water. Now, as an extra step that you might have to take, you would have to get some distilled water, and you'd have to rinse the sand. Now, the reason why is because there might still be some salt that's actually on the sand when you are actually doing your filtration. So your filter paper is here. That's your filter funnel. Okay. So you may actually have, right, you've got your sand as a residue in there. You may actually have some salt. So if you add some water and you just basically rinse it through, any remaining salt will just trickle through. So if you've got some salt that's left over, that salt will just dissolve in the extra water, and it will fall through the funnel for you to collect within the piece of apparatus that is containing the filtrate. So do remember, if you are in that situation, to rinse the sand with water. And then what you can do is you can then dry it in the oven. Why would you find a warm place to dry it? Because you've got sand and you've got water. So if you have a warm place, you just basically, in effect, drive off the water, and you have your sand. It's just sand. Now, an issue that you could actually be facing in an exam is you could actually be facing a situation where both the solutes, both the substances that you want to try and separate out, are both soluble in water. So a prime example is salt and sugar. If you use water, salt and sugar dissolve in those very, very well. So what you need to do is you actually need to use a different solvent. So you need to propose a different solvent. Now, ethanol is theoretically something that will dissolve the sugar, but not the salt. The reality of the situation, I'll be honest, I've tried this time and time again. It doesn't actually quite dissolve it, dissolve the sugar as much as you would want to. But in theory, it does actually work. It does actually work. And I've made, like, when I've actually tried this out, I've made small thin layers of caramelized sugar as a result of this. And what you would have to do is you would dissolve your sugar and salt mixture. So that's like the powders of the crystals of salt and crystals of sugar. If you want to try and separate them out, dissolve it in ethanol. Now, in theory, the the salt will not dissolve. And if the salt does not dissolve, that means that you can separate it out as a residue in filtration. The sugar will stay in the filtrate of the ethanol. So just to be very, very clear on this one, you use ethanol, it dissolves the sugar, but the salt remains in the residue of the filter paper, in the filter paper that's holding it. Now, if you were to, there's a health and safety point here as well that they could ask you about. It's actually quite a really tricky question. If you do get it, you know it's quite unlucky. But there is a health and safety point of view because the ethanol is flammable, so you actually would have to put your ethanol sugar solution you actually have to put it above a beaker which actually has water. So this is effectively a water bath. In chemistry, you don't directly heat alcohols because they would just set fire, and it's a very, very dangerous situation to have. But what we can do is you can indirectly warm up the ethanol by just having it over boiling water. The boiling water is at 100 degrees centigrade. Ethanol boils at 78 degrees, so the ethanol will actually easily evaporate and boil. It will evaporate first and then it will boil. Okay, right, I'm going to move on now to simple distillation. So simple distillation kind of takes on that principle. So you've actually this is actually an alternative to evaporation for salt water, because effectively what you're doing is you're removing all of the solvent. But if you remove all the solvent, you're left with salt in your original sample. So it's the same thing in terms of what you want to try and do. But this is a distillation apparatus. So basically, what it is this: you've got to actually notice that this contains a tube over here, housed inside a jacket of cold water. Now, what does the cold water do? Well, it fills up from the bottom, and as it goes through, it warms up. Now, I'll tell you why it warms up in just a moment. But it warms up, so you get warm water coming out, and what you have is a constant supply from a tap of cold water in. So you've got a way in which you can actually transfer energy away from anything that is passing through this passageway. Okay. So that's quite useful, because if you have salt water, for example, it just contains salt and water. If you heated it, the water would actually exist as a liquid first. When you heat it, it would turn into a gas. So that's just the water. The gas, which is steam, flows down. It's the only place that it can go. It passes down this chamber. Now that's steam, that's water vapor. And as it passes through, it touches the walls of the inside of this piece of apparatus, which is called a condenser. Now, when it's passing through, the water particles actually have a relatively high store of kinetic energy. And basically, what happens is that energy is transferred to the cold jacket. So as that happens, the water vapor decreases in temperature, and what you then can find happens is that the water vapor, which is above 100 degrees centigrade, actually decreases in temperature to a temperature that's below 100 degrees. And when that happens, it forms a liquid. Above that temperature, it's a gas. So you then find that you condense the liquid, which is why it's called a condenser. Now, if you store a beaker, please make sure that you put the beaker so it's actually catching any of the liquid that's forming within the condenser itself. So if you store that, if you actually are able to catch that water, you've now got a supply of distilled water, and that is actually what distilled water is about. It's just pure water, and it leaves behind the salt in the original flask that you have, this round bottom flask. Fractional distillation is like a step up from that, because you can actually have a liquid, a sample of liquid, and let's say that sample of liquid has two different liquids that are very, very soluble with each other. They form a mixture, and they can't be separated out. You can't sort of like tilt it and just pour off one, leaving behind the other. Okay, a good example of that is ethanol and water. Now you can actually utilize the fact that ethanol has a lower boiling point than water. So if you were to heat up an ethanol water mixture from room temperature, the first thing that would come off is ethanol. Now, some of the water will actually go up as well, because the water will turn into steam, but the ethanol will actually be driven off first. And what actually happens is, when you have a fractional distillation, there's a very long column that you stack on top of the heated mixture. It's stuffed with glass beads. So effectively, these glass beads also warm up. Okay, and so effectively, what happens is, if the ethanol touches the surface of the glass beads, and the temperature of the glass beads is higher than the boiling point of ethanol, which is 78 degrees centigrade, the ethanol will kind of like want to try and form a liquid and condense, but then it zips back to being a gas, so it passes through. If you have a temperature which is like say for example, if the temperature of the inside of the glass chamber, the glass column with the beads inside, let's say for example, for all intents and purposes, just for sake of argument, it is 80 degrees centigrade. So if it is 80 degrees centigrade and you get an ethanol molecule hitting the glass beads, it will evaporate immediately, because 80 degrees is higher than the boiling point of ethanol. Now, if a water molecule actually rose up and hit that 80 degrees, what would actually happen? Well, the 80 degrees is actually lower than the boiling point of water. So effectively what would happen is you would actually have a cold surface, and the cold surface would then draw away energy. So energy would be transferred away from the water molecule, and the water molecule would condense and it would return back. So you've got a situation then that you can actually uh, exploit. You've got the ethanol, which can pass through, and it will pass through, and it will continue to pass through as a vapor. And over here, you've got the water, which will try and pass through, but it will then be returned back. So you've got water flushing down, you've got ethanol passing up, and that's a great way of separating it out, because then if you have that hooked up next to a condenser, the only thing that you've got passing through right at the very beginning, once everything is warmed up and you've actually got vaporization of ethanol, is the ethanol itself. So the ethanol will then start to trickle through, and the water, when you set it up right, the water will actually just trickle back. So that's the ethanol passing through, and the water will actually just trickle back, and that is what separates, that process is what separates out the ethanol from the water. So that is fractional distillation, and fractional distillation is used in industry to refine petroleum. Okay, but you can also use fractional distillation to separate out ethanol that is made by fermentation. Ethanol is an important fuel, and it's also an important solvent as well. So it's a really important process to make. Paper chromatography, right? Okay, so if you have a mixture of substances and they are soluble in a in a solvent, for example, the substances that you have in ink, then what you can do is you can actually use another solvent to try and separate them out. So here's a dropper with ink, you put it on the filter paper, and then if you continue to add drops of water, eventually what happens is you get this like separation. Now you can see that the different substances actually separate out at different speeds. You've got this yellow one which is moving along really, really hurriedly. You've got, let's get a different color there. So you've got the yellow, which is speeding along. Then you've got red. The red substances are kind of like at the halfway pace. And then you've got these blue substances that are hardly moving at all. And the reason why is because there are two things that are in effect here. But I'll talk to you about that in a second. So you must make sure that you do have to be able to give these stages. And sometimes this paper is done in a flat way. Other times what happens is you actually have paper in effectively a tank like this with a lid. There you go. So you just fill it up with solvent. Talk to you about the needs and the requirements in a second. But you basically fill it up like that. And you make sure that you don't have your solvent submerging the points, and then you just effectively can analyze it that way. And the way that we do it is like when you're doing an analytical chromatography, which is the process that we're talking about, you would have like your mixture, and what you would want to do is you would want to actually see whether you could identify what's in that mixture with some pure substances that you would run in the chromatogram at the same time. Use a pencil line, by the way, because you don't want to have it run. If you use a pen for the labels and the line, then that would interfere with your chromatogram. So sometimes it's done like a flat way like this. Sometimes it's actually done in a ring like this. Same thing. You get the same results. And over here you can actually see that this was your mystery X, and it actually has B in there. It actually has pure substance A. Sorry. It actually has B. When we look at the distance that the pure substance B has travelled, it's the same height. Same thing with D. So this pink substance, which is separated out from your mixture of dyes, is D. Highly likely to be D because that's actually the same height as D in the same chromatogram. It's got some kind of mysterious substance there. We just don't know what that is. But it's also got A as well. So it's definitely got A, it's definitely got B, and it's definitely got D, but doesn't actually have C. Doesn't have C. Okay, so this C was like a mystery substance that we ran along with that because we wanted to try and figure out, right, okay, does this actual X mixture, does that actually have C? So we can use chromatography to identify what is actually in a mixture of substances. Okay, right, so going to move on talking about why chromatography actually works. The reason why it works is because there are actually two things in play here. You have an attraction between the substances in the ink and the substances of the paper. And you also have an interaction between the substances in the ink and the actual solvent that you're doing the chromatography in. So if your actual substances are more soluble than others, they will actually run up the paper or run along the paper faster than other substances that prefer to be on the paper and are attracted to the paper and less so attracted to the actual solvent. So the more soluble the substance is in a solvent, the further it will travel up the chromatography paper. That's up if you're doing the chromatography like that, or it's more along if you're doing the chromatography in that direction. Cambridge actually want you to identify substances in a colourless mixture. So you basically need to have something that brings those substances into a way in which we can actually see them. So there's two different ways of doing it. You can actually spray it with something called a locating agent, and that will be one example is called ninhydrin. So that would actually show up the spot, so you can actually see something that was invisible before and is now actually turning visible. The other way in which you can actually do it is you can avoid spraying the substances on your chromatogram. You can actually put them under UV light and see if any of the substances actually glow in ultraviolet light, and if they do, that's what we call fluoresce. So you can actually run chromatography on invisible substances, and a great example of invisible substances that you do chromatography on is amino acids. Now, when you're analyzing at a higher level, you have to look at something called the retention factor, which for other examples, it's actually called the retardation factor. It's actually an RF value. Okay, so the RF value is actually equal to the distance. So I'm just going to look at B here. So it's the distance that the substance travels. You measure that from where it was originally and the starting point, divided by the distance that the solvent travels. So that's 2. So it's always a number that's between 0 and 1. And when you get that ratio figured out, you can actually then compare it against data tables, and that will then help you identify what you actually have. Okay. So it's just a bit of extra info just for if you're quite interested in it. But this material over here is not actually something that comes up in the exam. And I'm just going to sum things up now. So for the core, make sure that you know what the definition is of mixture, solution, solute, aqueous solution. Aqueous solution is something that's dissolved in water. A solution can be more generic. That could refer to propanone as a solvent, can refer to ethanol, and so on and so forth. 3 examples of solvents: propanone, acetone, white spirit is another one, and ethanol would be a good one, as well as water. State that most solids become more soluble as the temperature of solvent rises. I think we've done that. Pure and impure. Pure only contains one type of particle, and remember that we could be talking about a molecule as well as a collection of atoms. Or the same, or a collection of particles that have the same atom, the same particle with the same proton number, so it could be an element. So pure substances only contain one type of particle. Impurity, well, obviously, it's something that contains more than one type of particle. Give examples where impurity is very important: baby foods and also medicine as well. Okay, so food and medicine. Say how melting points and boiling points change when impurity is present. The melting point deflates and the boiling point rises. Decide whether a substance is pure from melting and boiling point data. So the key to look out for is it clear and is it sharp? That is a pure substance. Okay, if it's broad and if it's over a wide range, like if the TM melting point or the boiling point is broad or has a wide range, then that is something that is impure. Describe these methods for separating mixtures. Sketch and label the apparatus. Please make sure that you know how to label each one. That definitely comes up in paper 6. So filtration, crystallisation, evaporation to dryness, simple distillation, fractional distillation, and paper chromatography. Explain why each of these separation methods works. So we've been through that in the video. If you need to go through that again, then do so. Say which method you would choose for a given mixture and why. So remember that table that we went through. So like say, for example, if we needed to separate out a solvent from a solution, you would use simple distillation. Okay, there's about 6 of them that you need to take yourself through. And what else we need to know? Say which method, we've done that. Identify the coloured substances present in the mixture using chromatography. Remember, what you make is a chromatogram. There's an A and an O. Extended, we'll explain what a locating agent is. That will highlight invisible substances that you've separated out from a chromatography experiment. How do you carry out chromatography to identify colorless substances? You can use a locating agent, or you could use ultraviolet light. You need to spray it with ninhydrin if you want it to come out and be visible. There's another one that you can use. It's called iodine. You can actually use iodine as well, just to keep the chromatogram with the invisible spots in an environment with iodine. And more often than not, you actually then find that the iodine binds to the spot, so it makes it visible. Define RF value. It's the distance that the substance travels from original spot divided by the distance at the solvent front. That's the top edge of the solvent at the end of the experiment travels. So there's no units because you're dividing distance by distance. Identifying the substances in a mixture given a chromatogram and a table of RF values is a very, very common question. I'm going to delve into this question over here. Just to finish off, chromatography experiment, 8 colored substances were spotted onto a piece of filter paper. 3 were the basic colors, red, blue, and yellow. The others were unknown substances labeled A to E. This shows the resulting chromatogram. Which one of the substances, A to E, contains only one basic color? So let's just have a quick look at that one. Well, substances A to E, well, B definitely contains one substance only. So that would be the answer to that, which contains all 3 basic colors. So let's identify this one. So that is in there, 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 and there. This one, this basic substance, is in there and there. This one over here is in there and there. So clearly the answer is A for the second one. The solvent was propanone. Which of the 3 basic colors is the most soluble in propanone? And to answer that, what you have to do is you have to look at which one traveled the most. And the answer is the red one. Okay, so I'll just finish off the colors on that because people might be quite confused by that. That's red. That would be red. That would be red. That would be red there. I'm just having fun now, coloring it in. That's blue. That'll be blue. That'll be blue. And that's blue. So that makes you, hopefully, makes it easy for you to spot what's actually going on. I'm going to end the video there. So I really hope that this has been really, really useful for you. Try not to get bogged down too much in the fractional distillation and the simple distillation, but at the same time know that there's loads and loads of marks, particularly with the practical papers, on an alternative to practicals with those themes. Make sure that you can label them. So this one would be a condenser, for example. This is a thermometer. Okay, so make sure you can actually do that. Don't get caught out with anything like that. Okay, there we go, condenser. Okay, with an E on it. Take care. Thank you very much for watching, and best of luck with your exams. Bye for now.